Okay, we seem to have a lot of people now online, so I think we can start so that we don't delay your day or your evening. Welcome, first of all. Thank you all very much for joining. It's great to see yet again so many people here on the webinar. Today we have two presenters, both from the European side of the pond. We have Lucas Hauser, who is the R&D project manager based in the headquarters of Weidmann in Rapperswil, Switzerland. And we have a special guest, Yuri Shapilov, dialing in from Malin, Ukraine. It's great to have you with us, Yuri. Yuri's been a R&D director for Weidmann for many years, and we're very happy that he's able to join us today on the line. Today we're going to talk about hidden risks related to insulation. So all that exciting stuff, where you're hiding your transformer board in the factory, behind the racks and so on. We will go into all the hidden topics around what you should be doing with your materials. So with that said, one final bit of housekeeping. In the top right corner, you will see a question mark in a chat box. If you have any questions at all, please feel free to click there at any point during the presentation so you don't forget the question. Don't worry, you won't disturb Yuri or Lucas. I will get those and I shall do my best to get to them at the end of the presentation when we have 10-15 minutes to try to work through those. So feel free to throw your questions to me and I promise I'll do my best to get them out to our panel. So with that said, I will hand over to our team. I believe, Lucas, you will kick us off today. So I will see you all with this image on the screen at the end of the show and leave Lucas to explain that and Yuri. Thanks very much, and I'll see you at the end.
Okay, everyone, thank you for joining us. And on behalf of Weidmann team, I would like to start our presentation. And again, greetings from Ukraine. What we are going to talk about the moisture insulation in cellulose insulation material. And this will be some kind of part of our Weidmann Academy global approach, which is based on our knowledges, a lot of tests, a lot of reports, practical experience, educations. You already read a lot of books, Transformer book, a lot of articles from our colleagues. And based on it, we created the Weidmann Academy based on 3 pillars. First pillar will be the basic course, or it is a basic course for our internal staff, which we provide all our lessons to our workers, to our staff, engineers, designers, whatever. Then the special courses oriented for the really specific targeted group of people, like a designer, like engineers, like a technologist. And then we explain a bit more detailed, very, very important things, like for today, hidden problem with insulation or moisture in insulation. And as well, the training courses, which we kindly provide for the customer on request, or in case of any special interest, we can provide this in a very detailed manner with some experiments, with the explanation, with the examples of our materials, etc., etc. So we call it the Weidmann Academy. You see it under the roof, and on the frame of that, we would like to talk about insulation and moisture in insulation, which is quite interesting topic for us. So you will learn about 2 main components, water and insulation and cellulose. Then you will hear about the absorption of moisture and then consequences, how to protect it, and then what kind of expectation of lifetime expectancy will be explained later on. So, water and insulation, water and cellulose. This is two words which goes always together. You all know that we provide the cellulose-based insulation materials. It's different grades of paper, different grades of board, components, laminated board, etc. But all of them consist only of 2 main parts, cellulose and water. And to know a bit more about the practical aspects of the moistening of the moisture impact, you should remember about the structure of the cellulose fibers and about very important properties. So you know that the fibers consist of the cellulose, let's say chain of cellulose, and the chain of cellulose consists of the glucose molecules. And this chain has hydrogen group and hydroxy group. And these two groups really easily absorb water by creating these hydrogen bonds. And due to that fact, the fibers connected with each other in a very good manner. But due to that fact, we know that the cellulose fibers absorb water easily, and this is the natural process, very, very natural process. Each and every papers and board and even textile absorb water from the ambient condition, and this is just a natural process. So you should remember this, and on the next slides you will see the interconnection between fibers and water amount inside of the during the production and during the application of the insulation material. So to produce paper or to produce transformer board, as you see on the picture, most probably you're aware about these processes, but it's very simple to explain. So we get the cellulose in bales on the factory, so it's a very solid material, looks like this, and then we need to put it to the pulper, to put water and to put pulp and then mixing. So in that stage, we apply about 90%, 95% of water and only 5% of pulp. So then all this mixture goes through the process, through the paper making process. We use refining for the to create some special surface of the fibers and to increase the connection. Then we need to clean this mass and we use the cleaner for that. Then we make a formation. During this formation, we already put additional amount of water, and this is already 99% of water and only 1% of fibers. Then we create a fiber mat or wet sheet on the making roll, and this making roll or this wet sheet already consists of 70% of water and 30% of fibers. Then we have to dry it either in the hot presses or in the drum dryer if we produce the paper. And final product as a paper or as a board consists of 4 or 5% of water, and the rest, this is the fibers, 95% of fibers. So you see this interconnection from the very beginning where we had 95% water and 5% fibers, and then totally the opposite, 95% of water, of fibers and 5% of water. And basically all material, typical paper or typical board, cardboard or offset paper or printing paper usually consist of maybe 5-6% of water, and the rest, this is the cellulose fibers. And this is absolutely normal, but not for the insulation material, because to use it properly in the transformer, to give them the really excellent insulation property, we need to remove the rest of the water almost to the 0%. Because if we have some water inside, that will be a lot of different things, a lot of different problems, which you will hear in a couple of seconds from Lucas. But just remember that cellulose is really strongly hydrophilic. They absorb water easily from the air, from the ambient condition. So just be prepared for following explanation from Lucas. What does it mean absorption and what will be the consequences?
Thank you, Yuri, for that great part. Now I will take over and we will have a look at moisture absorption. I want to structure this part into some categories, some questions that we always hear and want to answer for you. The first one have a quite distinct answer. How is water coming into cellulose insulation material and how can we measure it? However, questions 3 to 5, how much water is absorbed, how fast is it absorbed, and how fast can we remove it? Here, the answer often starts with the words, "it depends." And today we will try to answer the question what it depends on for you to get a feeling what is critical to care about. And finally, question number 6 is asking what are the influences of this water content? What does change in my geometry? How do my electrical and mechanical properties change with regards to the water content in my board? Also here we have distinct answers. So let's go to the first question, moisture absorption. Now, you might think that we have a little typo in here in the word absorption, but actually that's not the case. So when we talk about moisture absorption in overall, we mean just water going into the board. However, this process in nature is separated into two processes. On the one hand, there is adsorption of the humidity in the environment to the surface of the board. And secondly, we have diffusion of that humidity into the board. Both of these are governed by temperature because many natural processes, if not all of them, are governed by temperature. But the adsorption is also very much defined by the ambient conditions, while the diffusion depends also on the pressure the material is within and whether or not the material is oil impregnated. We will see later what the influence of such an oil impregnation looks like. Secondly, how can we measure the water content in cellulose? Now, there are different methods, and I want to highlight here the two main methods that Weidmann uses to dry and also to measure the water content. The first method is quite simple. You take an oven and a vacuum oven and a scale. And what you do is you take your sample, you weigh it with the conditioned state, then you go into the forced air circulation oven, dry it for 1 day, then dry it in the vacuum oven to reach minimum value, and in the end, weigh it again. And the difference in weight will then be the water that was removed and can be calculated back to a water content. Now, this is a global value that just says this part of sample had this content, but there is no possibility to determine the exact location at a certain water content. If you want to do this, for example, you want to know the humidity of the different layers of laminated board, then you need to use coefficient titration. Here we can take a very small amount of material and test that, and then we know exactly the water content at that specific location. However, this method, when you want to use it for a global value, you really need to take samples at many locations and then use statistics. What is also quite critical here is that due to the small amount of sample that you use for this test, it is a method where sample generation has to be done with really, really keen eyes. Many of you know this, but I state it again, 90% of mismanaged sample readings come from sample preparation. And so this is really a test where you need to be very careful in handling, use gloves, don't expose the sample to environmental conditions, but really make sure that in between sampling and measurement, there is a small time and you have the control over the ambient conditions of that sample. Also in that method, of course, in the end, you have to heat the sample to release the water. Next, you can see the Jeffreys diagram, which is a keen way of answering the question, how much water is absorbed? You can see on the x-axis, you have the relative humidity, and on the y-axis, the resulting water content in paper or board. The different colors of the graph show the different temperatures the material is in. As you can see here, all of these are ambient conditions that matter, the temperature and the relative humidity. So if we say that we have board, paper, and laminated board stored in a room with 50% relative humidity and roughly 20 degrees Celsius, what will be the water content in those samples? Please take a moment and think about this. It's different. It's paper, one is board, one is laminated board. If they're all stored at the same conditions, what is the water content that we can expect? As you can see here, the equilibrium water content of low density board, of high density board, of oil impregnated board, of non-oil impregnated board, it's all about roughly 7, so slightly below 7, as we have seen in Jeffrey's diagram. So when we leave enough time to the material, they will all reach the same equilibrium humidity. What is very nicely also to be aware of with this graphic is that the oil impregnated sample and the non-oil impregnated sample reach the same water content. This means the water must be able to go into places where no oil is and where oil will never be. Because if there would already be oil, then the water could not go there. And so this shows us really that the oil and the water go into the material, yes, but with different processes and to different locations. And so this is important for you to remember. When we give enough time for the equilibrium condition, we always reach at similar ambient conditions a similar water content. So then the question remains, but how fast is it absorbed, and what does this absorption rate depend on? And here we have some distinct factors which we are going to look at next. It's for one, the thickness of the board, and with that also, of course, the size, the density, the temperature, whether it's oil impregnated or not, whether there are glue lines or not, and as so often, the relative humidity of the ambient conditions. So here we can see a graph that shows you the influence of thickness with regards to water absorption when we expose them to 23 degrees Celsius and 50% relative humidity. You can see that the thicker the board, the longer it takes for it to reach equilibrium condition. Similar to this, we can see that at the same conditions, a board with 3 millimeter thickness will have a faster equilibrium moisture content at lower density compared to high density material. Next up, we can see that also temperature is of course critical. I will iterate this many times today. Most natural processes are in a way influenced by temperature. And we have here higher temperature means higher movement of the atoms. And therefore also here the case is that with higher temperatures, we reach equilibrium condition faster. The oiling is quite drastic. So here you can see a 3 millimeter board at ambient conditions like before. And you can see that when we do not oil impregnate it, we have some 7 to 14 days to reach equilibrium condition. Whereas even after 28 days, we are far away from this point. So the oil really hinders, especially also the diffusion, because many of the spaces the water wants to go through and wiggle around are already occupied in a way of moving through, not with the same attachment points. Next, we have the glue lines. You know that Weidmann will produce laminated board if the thickness requirements get big. However, what is very crucial to know here is that these glue lines, especially the polyester ones, act as an oil and moisture barrier. You can see this nicely on the left-hand side, where the top picture has some whitish, brownish light coloring, And we see that this coloring can only be reduced from the sides, because from top and bottom there is a blue line, which means no water can penetrate through it. For these structures, and due to this assessment, all the big clamping rings, barrier boards, and so on, the real massive structures, are equipped with drying holes and impregnation holes. They are the same and they have the same task: to get moisture out of these channels and oil into these channels to overcome the problem with glue lines. Now that we know how it takes up water and what governs its processes, the question is, how can we remove it? And here again, we can see that, of course, the thinner the sample, the faster it is dried. However, what is also important is the area, because we have the diffusion process which needs to transport water to the surface. The distance of diffusion is critical. And with this 15 millimeter thickness, we are always quick, while with this square, the area in the middle remains quite humid until everything is then out. Next, I want to highlight the importance of pressure. So if I want to not expose my material to heat, and I say, well, I will just reduce pressure to dry it. How beneficial and successful is this? You can see on both sides we have a quite low pressure of 0.5 and 1 millibar, but the left-hand side is at low temperatures while the right-hand side is at high temperatures. And we see that the 1 millimeter board at low temperatures takes hours to dry into an area of roughly 1% water content, while when we have temperature and pressure, this doesn't take more than 1 hour. So with this, we can look at the consequences of moisture absorption. First of all, it's important for you to know that due to the assessment that we have individual paper sheets that are stacked on top of each other to make the board, we can see that within the sheet, where we only have the fibers, we have quite a small degree of swelling, because the fibers which are covalently bonded will not swell so much. However, in between the individual paper sheets, we can have these hydrogen bridges and water coming in, which pushes the paper leaves out and generates thickness. So a general rule of hand is kind of 10 times more swelling in thickness than in length or width. What is also crucial is that the last step is this hot pressing of our material, and there we really force it into this state. And so whenever we cycle several times through shrinkage and swelling, this leads to a small net shrinkage, because the original state can really only be generated by this hot pressing. Now, what happens if we have assembled a part at ambient conditions that are just normal, 20 degrees, 50% relative humidity, and that part was really stored there for some time and gained 6% water content. Now we put it in the oven and dry it. And what happens is we have a shrinkage of the whole assembly, where the spaces shrink more than the inner diameter of the cylinder, generating a loose assembly. It is therefore critical to always know what we do and when and why and how to account for it. The reverse example is we have an oven-dried assembly and we expose that to relative humidities of 20 degrees and 50% humidity. Here we get a swelling, and again due to the same reasons, and you can see that now we don't talk about circular stuff anymore. It is really deformed. So when handling material, we have to be aware of these geometrical consequences the material will have by just coming in contact with ambient conditions. When molding our material, this anisotropy of the three room directions shows again. When we dry this, we can see that any concave mold area will be delaminated while the material gets pressed to convex parts. So also when molding our material, be aware of this and account for it previously. Next, we go to the dielectric properties. Our material excels at really dry states. And on the right-hand side, you can see oil-impregnated paper that was tested for its loss factor, ton delta, and breakdown voltage. And we can really see that roughly at 1% humidity, water content, these values start to go out of the area that we want them in. So above 1% water content, our losses get higher, and above 1%, our breakdown strength is reduced. And again, you can also see here, this is again temperature dependent, of course. Next, we have a look at the mechanical properties by looking at compression, tensile, and bending. In these three areas, we can see that when we have the water out of the material, it becomes more rigid, more really less elongating, less ductile. It really becomes rather stiff. And so when we have it dried, there is a high force needed to compress it compared to the conditioned one. The tensile properties are roughly the same, but here we can really see a difference in fracture image because the conditioned one will really have more elongation, somewhere about 3.5, while the dried one is struggling to get to these values. And again, for the bending strength, we see that if we have a dry material, it is much more forceful and has higher bending strength than the conditioned one due to the water it contains. So we can really summarize this, that water in cellulose is associated with changes in geometrical dimensions, mechanical properties, and also electrical properties. And it will always react to its environment and the conditions it's in. And therefore, it is crucial that we learn from Yuri how to protect our material from moisture.
Yeah, thank you, Lucas. That's really incredible behavior of the fibers and water. And I believe most of you will ask ourselves, so why don't you produce the board and paper with the very limited amount of water, close to zero already, directly from the paper and board machine? And again, the answer is it is theoretically possible, but practically makes no sense, because this is just a question of time when paper and board gets relevant or equivalent quantity of moisture. That's a question of time. So you can impregnate it, you can increase the density, you can increase thickness, you can increase whatever you want, but sooner or later, if you let them lay out without any packaging, without any secure storage, just on the ambient condition, in a couple of days or weeks, depends on the thicknesses, density, depends on the property of material, you will have almost 6-7% moisture inside of your paper and board. So how to protect this? Of course, we need to have a proper packaging. That's what we absolutely necessary to have because of ambient condition influence. So if you don't package our material, the sunshine will put efforts on this. Then the rain, the humidity exchanged, and moving of air will create a lot of diffusion of the water around our material, and then absorption will be differently from the different part of the material. Even worse, if we packaged it properly and put it again on the not proper storage with the sunshine, with the sun heat gradient. So inside of this packaging will be also movement of the water or movement of the moisture, if you like, due to diffusion, due to different gradients. And such movements could create huge problems, like deformation of the materials due to swelling from different sides. Imagine this warped materials. If you put the pie of transformer board without packaging for a couple of weeks out of the storage. Believe me, you will have such funny structure, and this funny structure, warped material, will create a lot of problems with the cutting, with the gluing, with the fixation of the elements on the washers, whatever. So it will be absolutely close to impossible to produce the good product from such warped material. As well, if you have thick laminated board and put it somewhere without proper packaging, the water will attack from the edge and try to go inside of the material, as Lucas explained already. And it will create also some swelling effect inside of the material already. And such swelling effect will try to delaminate our material. And it will be some very, very small or micro cracks inside of the material, which also could create some questions. So really, you will have a lot of headache if you don't package and store properly our material. So packaging is the first step which we have to apply directly after production. And Weidmann made a lot of experiments with different packaging materials. So you should be absolutely sure that we provide the best packaging. So we used a good material for that, special film, polyethylene film, couple of layers. We put desiccant inside. Desiccant, this is just a substance which absorbs much more faster water and much bigger quantity than our material. So we usually put some kind of silica gel to the package of the components, for instance, because components itself absorb water much faster than dense board, for instance. So we have to properly package it. We do impregnation of the cylinders, for instance, and this protect not protect from water absorption at all. It's just a prolonged time for the absorbing water. So if you have oil impregnated cylinder, it does not mean that you will not have water inside. You will have, just a question of time. So if you get a properly packaged material to your storage, don't put it outside of your storage. Don't put it on the sunshine. It must be also properly stored area. And there is a three simple rule, or three simple words: dry, cool, and dark. This is the place where you should store the insulation material before you are going to use it. Never open the packaging before using. So if you're willing to have board material in 2 weeks in your production, just keep it in the original packaging, and only before a couple of days just open it and try to use it as soon as possible, as quick as possible. Don't put our material to the direct sunlight, because it will create also questions with the, for instance, the bleaching effect, which may be not so important because everyone put insulation material inside of transformer and no one else seen in a couple of decades. But sunshine and direct, maybe even heating of our material will create another question, the losing of degree of polymerization, which is another story. Lucas will tell you in a couple of seconds. And of course, if you have a damaging packaging or damage somehow during the transportation or during the handling, please put something, cover it, like the polyethylene film, or wrap it once again. Don't store material with a damaging packaging. This is a critical for the further processes, because of the swelling, moisture absorption, and this again just a question of time when, because you already know that how many, from the Jefferson diagram, it will be about 6-7%, depends on where you located, in South Africa, in Ukraine, in Canada, or whatever. It depends on the ambient condition. But always, this is the question of time. And I turn back again to Lucas, and he will tell you a bit more interesting information about what does it mean DP and how it's related to lifetime expectancy and moisture at all.
Thank you, Yuri. So as you have heard, the degree of polymerization is a word that is always neatly and nicely linked to the lifetime expectancy. Let me quickly reiterate what the degree of polymerization is and how we get there. So the degree of polymerization is the amount or the number of molecules that are linked in this chain that forms the fiber. It is not the fiber length. It is the length of the molecules, the number of molecules that make up one fiber. Now, there are different methods to use there to evaluate this. There is tensile strength that is also linked to this dP, and you can also, of course, by viscosity, find out these values again. But what is critical for us to know is that this fiber grows with the tree. And so we can state that as soon as this tree is cut down, this degree of polymerization will not increase anymore. It can only be decreased by processes. Now, when we talk about the dP of new board or paper, we are roughly in the ballpark of 1,200. There are some that are higher, some that are lower, but this is roughly the ballpark you can place it in. Now, when we say the material is at its end of life, then the degree of polymerization is rather 200, and it is very brittle. Now, what we can also see is that the degree of polymerization is visible. So the coloring of your paper and board will make it such that you can assess in a rough ballpark what degree of polymerization you are left with in a sample. Now here I would really love to hand you out some of these samples to fold them and unfold them, touch them and feel how they behave. But this is of course a webinar and all I can give you is the visual input. But as said, when we are coming to your site for a transformer session, we can give those samples to your engineers and then they really feel the difference. And I think this is a critical thing, because seeing with your own eyes, touching with your own hands, this is really a way of learning for many humans. So what is, again, here the question? The question is lifetime expectancy. And we can thank Arrhenius for his genius of finding the Arrhenius equation, which is an equation that determines the rate at which natural processes take place. Now we see that the rate is here this K, the A is a prefactor. Here we can state that this is mainly a material specific factor. Then we have the activation energy. This one is depending on the process that takes place. And we can see, as so often, the temperature that plays an influence here. This temperature dependent rate constant will allow us to plot our life expectancy against temperature, because we see that at lower temperatures this process takes place less fast, and at higher temperatures it gets faster and faster. So the question we have to ask ourselves is, which processes take place for the degree of polymerization to be reduced? And there are three distinct processes. The first one is hydrolysis. Hydrolysis uses the water or the acid part of the water to make the chain be disrupted. Now, very critical here to know is that this hydrolysis is an autocatalytic reaction, meaning the educts that it uses for the reaction generate the product, which again displays the educt for the next reaction. So the amount of water that you have in the beginning is kind of a head start for the degradation. And the least amount of water, the least big is your head start. So this is really why we need to have the material as dry as possible before we get in. because this reaction really benefits from any water that was still in. Then we have the pyrolysis, which is also a chain rupture that is governed by high temperatures, and oxidation. Here, I think you all know this image very well. When you cut an apple, you have two nice and white sides. You let it lay on the table and they get brown. So this oxidation, of course, needs oxygen. Now, when we look at the overall rate constant, we can divide this into these three processes, where we see that the oxidation is actually the lowest temperature rate, then the hydrolysis is somewhere in the middle, and pyrolysis really takes place at elevated temperatures, starting from 140 degrees Celsius. Now, with that in mind, we can ask ourselves the question, how do I need to dry my material to have the least amount of degradation? And this we can see in the next slide. First of all, when we have really moist water from the machine and the water is free, we can just press it out, no harm done to the material. As soon as we get drier and drier, removing the water gets more and more intense, and we start to see degradation and oxidation. On the right hand, you see the graphic, and you can see in blue the lines at 105 degrees Celsius, in green at 120, and in red at 140. The dashed lines show the vacuum state, and as you can see, at 140, our degree of polymerization just drops because we have a large contribution from pyrolysis. If we reduce temperature, we can reduce this effect. And secondly, if we compare vacuum to forced circulation, we of course can see that in vacuum there is no moisture and there is no oxygen. So any moisture that is present will be sucked out, any oxygen that is present will be sucked out, and therefore hydrolysis and oxidation are slowed in the rate. Now, if we plot the degree of polymerization as a function of moisture content, and we ask ourselves what is more important, that it is really dry or that the degree of polymerization remains very high, we can see that actually if we are too high in water content, meaning between 2 and 10%, we have a very low lifetime. Then below 1%, we enter a range where the age becomes really nice, some 40 to 50 years. But if we dry it too hard and we get to a really low degree of polymerization, we see that it starts to reduce again. Nevertheless, you can really see in this graphic that it is crucial that we are dry, and we should not fear an additional drying cycle if done correctly with the minimum amount of degree of polymerization decrease, because the water and this autocatalytic reaction are really the detrimental factor in lifetime expectancy. So, as a message for you guys to take home, and really nicely summed up in this graph, we can say, what is required to do a lifetime expectancy in the maximum sense? And the answer is water and heat reduce the lifetime expectancy significantly. And therefore, if you want to have a long-living transformer, you have to keep it cool and dry. And with this take-home message, I want to thank you all for your attention. It was a pleasure having this webinar for you. And if you have any questions, feel free to let Francis ask them to us.
Thank you very much, Yuri and Lucas, for the interesting presentation. It was, yes, it was great. And our audience seemed to be hanging in there. I was about to tell you you're going a bit long, but that's fine. It's all good. You wrapped up just in time. We do have a bunch of questions, so I want to try to get to them. First question, and Yuri, Lucas, feel free to jump in with whoever wants to answer, but maybe Lucas, the first question I'll throw to you. It's about transporting the transformer to a power station or to a substation. And the question from the audience is, what is recommended, in oil or vacuum?
Thanks for the question. It's a good question because, as so often, you can kind of answer with it depends. Because it depends on the duration of the shipment, the location that you have to go to, the passing that you have to go through. Meaning that most transformers are too big to be transported as a whole, and also from factory acceptance tests, they were already oiled ones. So the easiest way, I would say, is to have the factory acceptance test done, drain some of the oil, controlled such that you know where you still have oil, remove all the bushings that are hindering your transport, close the transformer down with some Fulton bulk or similar, and have it shipped in the oiled state. This is, I would say, the easiest way. There are sometimes issues where you cannot kind of really nicely confine it in oil, or the transportation way is too difficult for this, and then you have to switch to vacuum. However, also with vacuum, it's of course very important that you maintain this vacuum at all time, that the sealing is well done, and that you have no contamination or water coming in. So I would rather tend to oiling in an easy way, but of course, as said, there are situations where you need to be able to go with either or.
Okay, thank you. And a quick question from the audience. What is the minimum moisture content for cellulose in ppm? Do you have any answer for that? Minimum moisture content for cellulose in ppm.
So my first answer here would be that ppm is the wrong scale. In ppm, we talk with oil, right? Some mineral oils, they have some 6 to 16 ppm, somewhere in that range. However, it is really important that you see that we state somewhere about 0.2 is where you can really achieve with vacuum clever drying. If you want to go down, for example, to 1 ppm, you would go into an area where potentially you have a lot of degradation to get to that level, if it's even accessible. And as a small add-on to the question, when we are already discussing these scales, right? If you look at the amount of oil in a transformer and the amount of cellulose in a transformer, and you remember that for oil you use ppm and for cellulose you use percentage points, then it becomes quite quickly evident that actually the large amount of water that remains in the transformer in service really comes from that remaining part in the cellulose, and that the oil is only 1 to 2, 3%, right? So this is why it's so crucial to dry the cellulose, because you can only dry it so far, and that you really have to do. And even if you do it correctly, the major amount of water in the transformer will come from the cellulose insulation.
Okay, thank
Just
you.
now from my side about this minimum content. Theoretically, you could dry up to 0, but again, it takes harder and harder when you draw down, when you moisture content drop down. So from the paper making processes and board making processes, when we try to dry out as best as possible, we need to spend a lot of heat and energy. As well, when you try to dry transformer or active part of transformer, this is a question of money, of course, question of time and energy. So do you need to dry it completely out? And then this is the question of time when moisture will come back, if you do not store this transformer properly or not assembled it properly.
Okay, I have two quick questions for you because we have a lot of questions here. So, Lucas, I want a yes, no on this one, please. Is
Very
moisture...
simple.
Yeah, of course. It's a marketing take on engineering questions. Are you saying that moisture is the most severe degradation mechanism experienced by cellulose? Is that what you're saying?
I would say in the standard practice, yes. But if you burn it,
Yes.
you will
No,
see.
no, you gave us a yes. Thank you. For now, we have that. I have a question for you, Yuri. Very quickly, please, how long can you store insulation? So we've talked about the practice when it's in a transformer and the conditions, but if it's in the factory, and please remember before you tell me that you can store it for a long time in the right conditions that Weidmann have shelf life guidelines for this.
You already answered.
Perfect. Okay. Then,
No, basically you can store it for endless, but the question is, again, the degree of polymerization will drop later on in the couple decades, and the moisture content, etc., etc. But friendly, you can store it for endless.
okay, that's not the official Weidmann line that you can store it endless. And just
not.
related to that, humidity. What level of humidity is ideal in the production shop? I don't know if we would have an answer to that.
So I think what is important to know here is that I would argue there is no overall climate that is perfect for every site. Because I would say that if you take out your oven, out your active part of the oven, there you can maybe try to have a climate that is very dry, some desert climate, so to speak, right? And you do this because the part comes out of the oven, you have to be quick, you want to have it absorb as least amount of moisture as possible. However, in those areas, the personnel, the people that work for you will have to have drinking breaks, cannot long work the same time. And so this is why I would say keep it in standard conditions, package the material as good as possible to protect it against those conditions. And if you have delicate processes, especially right after drying, think about just finding a suitable atmosphere for that one room, but not for the whole factory.
Okay, thank you. As always, we've got the natural ester question. So how do insulating materials in transformers with natural ester behave compared to mineral oil in the presence of water and air?
So I jump here again. So what is critical here is, of course, that scientifically we are really interested in all of these esters and the different effects, but we have to state that, of course, mineral oils are much more researched. Nevertheless, one critical point that I want to highlight is that the amount of water that can be present in mineral oil is lower than in natural or synthetic esters. Meaning that if I have my very dry assembly in the very dry oil and it's mineral oil, not a lot of water will migrate into the oil. However, in the natural and synthetic esters, because they can accept more water, there is some post-drying to a certain degree because the oil can take up some of the water that is in the cellulose previously. So with regards to moisture, actually these new oils that are a little bit more accepting to moisture are good for the cellulose itself.
Okay, great, thank you. One question, not sure if we want to answer this. Is there a quick method, not necessarily as accurate as Carl Fisher, but more practical to measure moisture content in insulation that arrives at a factory? Any test that you know of?
I believe it depends on the moisture content, but the more practical way it's the weighting. It's oven drying. It's much faster and it's good enough to know. Of course, it is a lot of the other different methods which can be used for the wood preparation, for instance. This is some kind of measurements of the conductivity, but it's not really practically for the insulation material. It's much more acceptance for the measurement of moisture of cellulose, for instance, or wood itself, but not for the paper and board. I would say from the practical point of view, the drying, yeah, that's again end of questions. You see, but drying in the oven and calculate the different weights before and after will be absolutely enough.
Perfect. Okay. And I will go one last question. I know we have a lot of questions that we can't get to, but you do have the contact details in this presentation of Lucas and Yuri. We will distribute a PDF of the presentation, and there'll be a link to the recording as well for those that asked that. Final question, what are the consequences, and this is a transformer manufacturer, what are the consequences of leaving an impregnated power transformer pressurized with dry air inside its tank without oil for several months? So it's a stored impregnated power transformer that's pressurized, dry air inside the tank without oil. Any quick comment on that? Because I know we're running out of time and you all have meetings to go to after this.
If the transformer is perfectly sealed and the dry air is really dry, and you have already the barrier by some varnish of the part or even first time impregnation, you can store it quite some time, but just be sure that you really have it sealed, right? So this sealing is important there, and the dry air has to be dry, because if any contamination or moisture can come in, that's the risk.
Okay. Thank you very much.
Just because of the nature of cellulose fibers. Again, don't forget this. This is the natural process.
Yeah.
It's a question of time only.
Well, with that said, I would like to thank you all for joining us today. It was a pleasure to have you all here. As I mentioned, feel free to reach out to Lucas and Yuri, although if you all do, they're going to be busy for the next couple of weeks. But I apologize if we didn't get to your question, but feel free to reach out to either Yuri or Lucas or your other contacts at Weidmann, and we'll try and get you an answer to those questions. We look forward to seeing you all again on the next Weidmann webinar. Thank you very much for your time. Thanks for joining us, and look out for our email with the link to the webinar details. Thank you, Yuri. Thank you, Lucas. Enjoy your evening or the rest of the day if you're here in North America. Thanks very much. Bye-bye.
Bye, everybody.
Bye-bye, everyone.